In this section, I'm going to talk about pharmacokinetics, pharmacodynamics, and also give you some samples of some really common math problems that should ring true to you, and definitely math problems that you should understand how to do to adequately prepare and pass the NAPLEX. So first off, some pharmacodynamic terminology, so agonist and antagonist. Hopefully you're well aware of these, but agonist is something that stimulates a receptor and produces a physiological response. An antagonist is a medication or a blocker that prevents or reduces a physiological effect from happening. Now, a partial agonist, so kind of a couple classic examples, or one classic example I think of is varenicline, which is Chantix. It's a partial agonist at nicotine receptors. It gives some stimulation, but a partial agonist often has the advantage of limiting a full agonist's effect. Another example I can think of is buprenorphine, and the way it works is binds up those opioid receptors and stimulates them to some extent, but there's really a ceiling effect of stimulation that happens, and it prevents other opioids from coming in and binding and providing that full agonist effect. Receptor affinity. So when we talk about drugs and how tightly they bind a receptor, that's considered affinity. So if it binds it very tightly, that's a high affinity drug. If it binds it rather poorly, this represents a more poorly binding drug. Now, how this has a role and how this plays out clinically and in real life is drugs that have a very high affinity generally are associated with a higher potency drug. Okay, if they bind things very tightly, that means that it's probably going to have a very high potency. In lower affinity type medications, it's going to take more of the drug to get a similar physiological response to a small amount of a higher affinity drug. So hopefully that kind of makes sense for you. Now remember, we've got numerous subtypes and of receptors, and we need to think about selectivity versus non-selectivity. So a great example there are the beta blockers. We've got beta 1 receptors on the heart, and a drug like metoprolol, atenolol, is selective for those beta receptors on the heart, more selective for the beta receptors on the heart, and less selective for the beta 2 receptors on the lungs, which a beta blocker can potentially reduce lung capacity, reduce lung functioning by binding up and blocking those beta receptor sites. Again, other examples, H1 versus H2, H2 receptors being in the gut more so, H1 kind of responsible for antihistamine effects and things like that as far as itching, allergic reaction. Another example, alpha subtypes, so having more alpha receptors on the blood vessels versus in the prostate and urinary tissue. Another example kind of where affinity, selectivity, and these kind of terms play a role. ADME, this is an important acronym to remember. So we've got absorption. So these pharmacokinetic terms definitely can impact the role that a drug plays within the body. So ADME is always terminology that displays what the body does to a drug. So, how well a drug is absorbed, that is dependent upon the body and what the body does to it. So an example here is vancomycin, very, very poorly absorbed through the GI tract. So that's going to limit its absorption and obviously limit its ability to treat infections in other places of the body if we don't get any absorption. Distribution, kind of similar a little bit to absorption, but as a drug distributes kind of throughout the body, that can be limited. And a great example there is the blood-brain barrier. If we're using an antidepressant type medication and it's got very poor distribution to the central nervous system and can't pass the blood-brain barrier, that's a potential problem for it because it needs to get to the brain for its site of action. Metabolism, lots and lots of examples there where genetic variations can alter metabolism, drug interactions can alter metabolism, and so on and so forth. So I think I've definitely covered lots of metabolic issues, changes via CYP3A4 and all those different mechanisms that drugs are broken down. And then elimination, of course, that's through the kidney and eliminating drugs out of the body through the kidney. So all of these can play a role on whether a drug's going to actually work, what the concentrations are in the body, and really, how long that drug is going to last in the body as well. Another important term, half-life, I want to talk about. So I would remember that little formula. So half-life is equal to 0.693 divided by the elimination rate constant, or K. It's a good one to remember. Some factors that might affect half-life. Formulation, again, are we looking at an extended release formulation that's going to slowly release in the gut over time? Elimination, this is probably the number one thing that clinically we can see happen with our medications due to the kidney function changing. Absorption rate, so again, if it's absorbed very rapidly versus very slowly, that can affect potentially our half-life. Distribution, so I kind of mentioned that drug interactions definitely can prolong the activity of a medication. Keep in mind that half-life affects dosing oftentimes, so if you've got a really, really long half-life drug, so kind of a classic example I think of is fluoxetine as far as depression, and there is a weekly dosing on that if patients want to do it. Most clinicians prefer not to do the weekly dosing on fluoxetine, but because of its really long half-life, you could potentially do that. Same thing with, a lot of the antibiotics have shorter half-lives, so we dose them twice a day, 3 times a day sometimes, and a lot of that's dependent upon the half-life of the drug. Of course, I would definitely remember the creatinine clearance estimate, and one really, really big mistake I've seen made, and I've made personally, is forgetting the 0.85 female factor. Okay? Definitely got to remember that. Volume of distribution. So this is defined as the theoretic volume of fluid that would be necessary to keep the drug at the same concentration. And the volume of distribution, if you're given a number in a question, in an equation, that's basically the way I think of it is kind of the spread of the drug throughout the body. How deep, how much volume, how much space can that drug get into? So in our kind of simple compartment model, an equation you might want to remember is the concentration is equal to the dose divided by the volume of distribution. And I think if we think about this kind of makes sense. So the concentration, so that's how much drug in a volume of fluid, is equal to the dose that you're given. So if you give a higher dose, you're going to have a higher concentration. That totally makes sense. And if you have a lower volume of distribution, so a lower volume that drug is able to get into and access, that will raise concentrations as well. So I just wanted to lay that out as far as volume of distribution goes. And I think remembering that simple compartment model is helpful to help determine volume of distribution and help us understand it a little bit better. Drug interactions. So this is something that, you definitely should know inside and out. You will be asked this. Enzyme inhibition in general will lead to increased concentrations of a medication. So, classic examples of enzyme inhibitors via 3A4, 2D6, these will increase drugs that are metabolized by that enzyme. Now, we can have enzyme inhibition in rare cases leading to reduced concentrations. And in that type of situation, we're going to be talking about prodrugs. So codeine and CYP2D6, tamoxifan's 2D6 as well, clopidogrel 2C19. So these require an enzyme to convert them to the active form. So in codeine's case, that's converted to morphine. And if we have a 2D6 inhibitor on board, we can prevent that conversion to the active metabolite. Therefore, that would lead to a reduced effect, reduced concentration of those type of medications. Alteration in the renal elimination. So a good example there is lithium levels can be increased by thiazides because they alter kind of what happens in the kidney and that elimination of the drug. Absorption, drug interaction considerations, classic ones, cholestyramine, sucralfate. These can really bind up medications and lead to reduced absorption, reduced concentrations. A couple other examples are those binding cations, calcium, iron, maybe throw in magnesium even in there, with drugs like tetracyclines, quinolones, levothyroxine maybe, again, leading to reduced concentrations. Absorption, alterations, so I kind of talked a little bit about those binding interactions that can happen in the gut. Questran and Carafate I mentioned on the previous slide. But we can also have kind of all these alterations of the GI tract in gastric bypass type situations. So this is where a significant portion of the gut is bypassed, and that portion of the gut may be very important for absorbing nutrients as well as medications. So something like extended release medications, they may not be as advantageous. They may not get adequately absorbed in a patient with a shorter gut. Another GI alteration is gastroparesis and that slow motility. We may end up with increased concentrations or increased absorption in that type of setting. So again, I would say that's not incredibly common to worry about as far as the slow motility goes, but it is something to think about clinically, and something to think about if a patient is now displaying toxicity of a drug they weren't previously displaying toxicity to. Gut transporter saturation. So this is an interesting example. Gabapentin has a dose-dependent absorption issue, whereas we get to higher doses, we may saturate that gut transporter. And this can lead to a little less bang for your buck as we escalate doses on gabapentin. So as we increase the dose of gabapentin, the relative percentage absorbed actually gets lower or reduces as that dose escalates. And that's because of that transporter that that gabapentin requires to cross the gut and into the bloodstream. Onset of action, important things to think about here. So IV versus oral versus transdermal. Important to remember how quickly a drug is going to have activity. So in a situation like opioid overdose, obviously we don't want a slow onset of action. Okay, we want naloxone to block opioids as quickly as possible. In the situation of an IV agent, obviously that's one of the quickest onsets of action. That goes immediately into the veins, immediately into the bloodstream, and begins to exert effects almost instantaneously. Oral takes a little while to get through the gut and get absorbed. Transdermal, again, they're typically a pretty slow onset by the time that drug gets through the skin and into the rest of the body. Another example, think of albuterol. We can take albuterol orally as a medication, but because of what we use it for, that doesn't make a lot of sense, and we like to minimize systemic side effects as well. So giving that albuterol through inhalation, that's going to give us a much quicker onset, as well as minimizing systemic effects, than it would through oral administration. So I think, other important things are the drug itself. Some drugs tend to have more quick of an onset. So drugs that are maybe highly lipophilic, for example, may get into the brain much quicker and have a quicker onset of action. Same thing with, kind of tying in that example of lipophilicity as far as the intrinsic property of the drug. Now, what impacts bioavailability? So the drug itself, the size of the drug, properties of the drug certainly can impact bioavailability. The delivery route is going to impact bioavailability. If we try to give vancomycin through the skin, vancomycin is a very, very large medication in relative respect to other medications. It has a bigger size. You're not going to get delivery through the skin. So bioavailability there will be essentially zero. Now, when we give vancomycin IV, then we have a much better rate of absorption there, of course. Same thing with giving vanco orally. We don't have great bioavailability, so the route of delivery can definitely significantly impact that. First pass metabolism is an important thing to think about. So in the situation of budesonide, here's an example where we use it to our advantage. Giving budesonide in something like Crohn's, budesonide has a very high first pass metabolism rate. So by doing that, we're limiting some of the systemic side effects of corticosteroids by not allowing a steroid to get into the systemic circulation. but we kind of maximize the benefit because budesonide orally, we want that to work in the gut. And in something like Crohn's, ulcerative colitis, that's a big potential advantage to minimize the systemic absorption and kind of maximize keeping that drug in the gut for the localized effect. Drug-drug interactions, drug-food interactions can potentially impact bioavailability. So thinking about something like alendronate, and that we don't give it with any food or meds, that could reduce bioavailability. Physiology, GI tract, this can certainly impact bioavailability as well. Now, I did want to talk specifically about changes in the elderly. We work with a lot of geriatric patients as pharmacists. There are kind of top candidates for polypharmacy and issues going on. And I think it is really important to recognize some of the physiological changes as we get older and how that may impact medications. So first off, I want to talk about GI tract. So we've got some reduced GI motility, which can cause physical effects as far as nausea, vomiting, potential for constipation. Reduced gastric acid secretion can also maybe reduce the absorption of some drugs. So iron, for example, is a good example that is generally better absorbed with a decent acid environment. With that GI tract change, we can also run into increased risk of higher pH and less likelihood of destroying those bacteria. Okay, so higher pH might lend more towards the growth of certain bacteria there. Distribution, so we've got increased body fat. For lipophilic drugs, so an example here is diazepam, there is a increased volume of distribution, and with that increased volume of distribution, there's potential for more and longer lasting effects from that diazepam. With increase in body fat comes a reduction in muscle as we get older. We generally get fatter and weaker as we get older. This is certainly a slow process over years and years and years. But with that reduction in muscle, certainly physiologically comes fall risk. One other thing I wanted to point out was creatinine. So creatinine is basically this muscle breakdown. And as we age, this creatinine may get lower. And that creatinine doesn't maybe necessarily mean that kidney function is improving. But what it does mean is that our reduction in muscle mass may be a little bit less. So somebody, a 25-year-old with a creatinine of 1.1 and a 85-year-old with a creatinine of 0.9 doesn't mean that the 85-year-old has better kidney function. And you can see that in our creatinine clearance equations. They take into account age. But I just wanted to point that out, that reduction in muscle mass can potentially increase or impact, I should say, that creatinine level. Kidney, oftentimes as we age, that kidney function declines. So reduced elimination of medications. That muscle mass component I did kind of talk about on the last slide there. There are numerous examples of drugs that are cleared primarily by the kidney. Digoxin, allopurinol, pregabalin, Lyrica, memantine, all sorts of medications that are cleared by the kidney. So definitely in an acute kidney function change, where maybe we jump from a creatinine of 1 to 1.5, you have got to remember to look at drugs that are dose adjusted based upon that kidney function. Liver changes. So with liver function changes, it's sometimes hard to know how this is going to impact drugs. Okay, so kidney, it's a little more straightforward. We've got dose adjustments based upon kidney function, GFRs, creatinine clearances, and in liver function, it gets a little more murky as far as what do we do here. We know that, in patients with significant liver disease, that sometimes it's recommended to avoid medications or use with caution in patients with liver disease. And there's really very minimal clinical guidance on what to do in this setting. But certainly I would recognize the fact that there could be issues with metabolism in our geriatric patient population. What to do with that exactly, we really don't have much for standards on making changes with liver function changes. Albumin, this is an important thing to remember in our malnourished, weak, frail, elderly patients potentially. That albumin can be low. When we've got highly protein-bound drug, highly albumin-bound drugs on board and using them in a patient, that lower albumin can lead to a higher free fraction. So this means we may have to reduce doses depending upon that albumin and obviously depending upon that clinical response and how patients are responding. Infection risk, so as we age, that immune system generally tends to fail us as well or not be as good and robust as it is when we are younger. You think of skin thinning, you think of urinary changes, you think of natural flora changing, particularly as we age. We may use antibiotics. Also in females, I think of the estrogen component contributing, helping that natural flora. Oftentimes we use immunosuppressant drugs, so in management of kind of some of those inflammatory disorders, rheumatoid arthritis, things like that. Using those immunosuppressant medications can put us at risk for infection. Nutrition, sometimes diet is inadequate, things like that. And antibiotic use, I kind of mentioned that already as well. All right, so let's slide into conversions and formulas that I think are very, very important for the NAPLEX. Temperature, I would definitely know how to convert from Celsius to Fahrenheit. I would also be able to recognize what's a fever versus what isn't a fever in Celsius versus Fahrenheit. There's numerous situations where I've talked about temperature, and one particular an example that just came to my mind was febrile neutropenia. So if they give you a temperature, you need to recognize that that is a fever versus not a fever. Okay, so definitely important to remember that, and remembering the conversion may also be helpful there as well. Body surface area, there's a few different formulas for body surface area, BSA. Some drugs are dosed based upon this, and you may have to do a calculation. So I would, just for safety's sake, have a BSA calculation or equation memorized. So this is probably the most simple one that I remember, and height and weight there are in centimeters and kilograms. Important to remember that. Ideal body weight, I think this is a pretty simple one to remember. So 50 plus 2.3 times each inch greater than 5 feet. So if somebody's 5'1", so that would be 50 plus 2.3 times 1. So 52.3 would be the ideal body weight in a male patient that's 5'1". So hopefully that makes sense and is pretty straightforward. Other kind of conversions, equations, that type of thing. Drops per mil, definitely something you should know as a pharmacist there. TPN, so that this is going to be important, obviously, for calculations and calculating energy requirements and things like that. So definitely remember kcals per grams. I think that's an important thing to keep in the back of your mind if you've got to do a TPN calculation. Got to know, grams to milligrams, liters to milliliters, centiliters. You've got to know all these different equations, conversions that are part of SI units and what that looks like. Also, I would encourage you to know some of the English units. So, for instance, 1 milliliter is equal to 30 cc's, which is equal to approximately 1 ounce. 1 pint, there you can see, is equal to 473 mils. 1 pound, as far as weight goes, is equal to 16 ounces. Kind of another thing to keep in mind. Other conversions, inches to feet. You should absolutely remember that. 1 ounce, 30 mils, I mentioned that. Teaspoon, tablespoon. Commonly you'll hear patients refer to that terminology, as well as sometimes clinicians too. And remembering what those equate out to is going to be very important in doing some of your calculations. 1 kilogram is approximately 2.2 pounds. It's an important one to remember. Weight-based dosing comes up frequently on the NAPLEX, or it should come up frequently on the NAPLEX in your calculations. 1 grain is equal to 65 milligrams. This definitely might come up on the NAPLEX. Honestly, in clinical practice, I can't tell you the last time I've seen somebody use the term grain. So I think that's kind of an older, dated term, but maybe those making the exam still like to throw that on there. 1 mil, 1 cubic centimeter, 1 cc. You remember, with abbreviations, we don't like to use cc because that can be confusing and interpreted as other things. So let's get into the calculations. And so I really wanted to show you some of these basic, simple calculations that you absolutely have to have down pat with the NAPLEX. And the reason why I wanted to focus on the basics was just not to overwhelm you and bring you down to the ground level. Because if you can't do these basic things, if these are confusing to you, you definitely need to spend a ton of time finding whatever math problems you can find and practice. So first example here, just calculating day supply. So we're going to apply 2 grams of Voltaren gel 3 times a day as needed. So in this assumption, we're assuming that they're using this 3 times a day, because we want to know the day supply if they use it as instructed. So 2 grams 3 times a day, so that would be 6 grams total. And so 6 grams per day, I think you can see that written out here, divided by, 50 grams is what we have total, divided by that 6 grams per day. That day is going to flip up to the top end, and that's going to give us 8.3 days. Rounding up, that would be approximately a 9-day supply. Rounding down, that would be a 8-day supply. So again, also look at what they're asking you to do, whether it's rounding up or rounding down. Okay. Now, many situations with day supply, we would round down, because ultimately they would not likely get 9 days out of this if they were using it. They would still be short 2 doses in that situation there. So definitely look at what they're asking for, and I think that will help you not go astray. Remember what the question is asking for. Weight-based dosing, something very, very simple. Again, I talked about some of those conversions. You need to know how to convert pounds to kilograms because most of our drugs now are based on kilogram dosing. So there we convert to 28.2 kilograms, and from that we get 28.2 times your milligram per kilogram per day, and we get 2,255 milligrams per day. And again, remember what the question is asking. I didn't put the question on here, but they could ask you, how many milligrams per day is this patient going to use? But they also could ask you is, how many milligrams per dose? And I solved that for you as well. So if we're doing twice daily dosing with amoxicillin, which is commonly done, you got to remember to take that final step. Very, very important. Compounding questions will absolutely come up. So we've got an 8 kilogram baby. So they were nice in this question, and they gave us the weight of the baby in kilograms, so we don't have to do any converting there. And we want an omeprazole suspension, 1 milligram per kilogram per dose, once daily. And we do have the day supply, so that's going to be important in how much of the drug we need. So, solving first, we need 8 milligrams per dose, which is a once daily dosing, so that's also per day. 8 milligrams times 14 days, that's our day supply. We're going to get a total of 112 milligrams. 112 milligrams, and we have 20 milligram capsule. We get 5.6 capsules necessary, but obviously in this case we can't use 5.6 capsules. We have to round up because we're going to need at least 6 capsules to get to that appropriate dose. Percent volume. So this is just solving kind of a combination of two liquids. So we've got ingredient X, that's sucking up 13 mils. Ingredient Y is going to be 30 mils. And then we're also going to add water because we want a total quantity of 100 mils. So with ingredient X, we are going to end up with a total of 100 mils. Ingredient X, we have 13. So what is the percent volume of ingredient X? Well, that's going to be simply 13 divided by the total quantity. So that's going to be 13% is of that compound, of that mixture, is going to be ingredient X. Ingredient Y, liquid Y, 30 mils, that's going to be 30%. As far as the percentage volume of each agent. Now you can obviously go ahead and figure out how much water and what percentage that would be as well. But that kind of gives you a sense of how to calculate percent volume. Percent weight is kind of the same thing. So let's say you've got 10 grams of hydrocortisone and you're doing this with Vanicream. To get a total quantity, you want to dispense 500 grams. So you look at what we've got, grams per gram. So we got 10 divided by 500, and that's going to be 0.02, which is equal to 2%. Ratio strength. So this is an example I think you should be aware of as well. This is used for very small and or potent type medications. So again, 1 to 10,000. So in that situation, what that's equivalent to is 1 gram to 10,000 grams, or 0.01%. So again, very, very small quantity. Another example here, 1 to 100. If that's used as a ratio, that's 1%. Okay. Now, parts per million, 1 gram to 1 million grams, often is expressed as milligrams to 1,000 grams, or 1 milligram to 1 kilogram. Again, 1 milligram is a tiny, tiny amount. 1 kilogram is a lot. I mean, that's 2.2 pounds. That's a lot of substance there. So parts per million, often in the drug world, isn't incredibly commonly used. It's oftentimes more used for situations of highly toxic agents. So things like, radon in the air might be measured in parts per million, where it's a very, very low amount of radon in the air. But again, one of those maybe highly toxic substance if it is at higher doses. Flow rates, absolutely, very likely to be asked a question on flow rates. So we've got an example drug there, 750 milligrams infused over an hour and a half, and that's in a 500 ml bag. So calculating this out, we give 500 mils over 90 minutes. That's a flow rate of 5.55 or 5.6 mils per minute. So again, they're not asking about the drug. They threw it in there, but really that's irrelevant information. So again, focusing on what they're asking for, that'll help you not get confused. And sometimes they likely will throw in information that you don't need. And this is an example for what they want here. Now keep in mind, they may say round to the nearest hundredth, round to the nearest tenth, and you definitely need to remember how to do that. So 5.6 would be rounding to the nearest tenth. Rounding to the nearest whole number, that would be approximately 6 mils per minute. Okay, so definitely look at what they're asking you to do and asking you to round to as well. All right, so here's a good example of a TPN calculation. So you have aminosin 8.5% solution. So that's going to be important for determining how much fluid you're going to be using. But first, we've got a target of 1.5 grams per kilogram per day, and a patient's weight is 72 kilograms. So we're given all the information to try to figure out kcals. And if you remember that conversion that I talked about, you'll definitely want to remember that for protein, 4 kcals per gram. Okay, definitely remember those as far as TPN calculations go. So let's figure out first here. We've got 72 kilograms times 1.5 grams per kilogram per day. So that's 108 grams of protein for the day there. So 108 grams of protein. How many kcals will this provide? We get 432 kcals. Now the second part of the question, how many mils of fluid will this provide? Let's take a peek at that. So we know that we've got 8.5 grams per 100 mils, because that's what percent solution is. And that's equivalent to, we want a total of 108 grams. That's what we have for our total daily requirements. And we want to figure out, we want to solve for X, how many mils is that going to take to get to 108 grams? So solving for X, swinging X over to the other side, flipping this over, we get 108 grams times 100 mils. The grams cancel out as far as the unit conversions, and that's sometimes a helpful trick to ensure that you're doing your math correctly. And we end up through this calculation with approximately 1,270 mils for our total amount of fluid that this aminosin solution would provide. Okay, so just a good example here of a TPN calculation and some of the different factors you need to recognize that goes into this. Now again, I will say, remember what they're asking you to round to. If they're asking you to round to the nearest 1,000, if they're asking you to round to the nearest 100, so in this example, it'd be 1,300 mils approximately, which is a good approximation. There's not a lot of difference clinically usually with 1,271 mils versus 1,270 mils, and really not even 1,270 mils versus 1,300 mils. Clinically, 30 mils probably doesn't move the needle very much as far as clinical management. So they may ask you to round to one of those, kind of depending upon what they want to do. But you got to pay attention and make sure you get that right, because you wouldn't want to make a mistake on rounding. Percent air. So this is something in measurement that you might see, whether it's using a beaker or weighing things. So we've got a technician. They measured out 67 mils out of a prescription in a beaker, which generally aren't supposed to measure things in a beaker. They aren't the greatest as far as accuracy goes. They're really meant for holding and mixing. Pharmacists then verified the quantity using a graduated cylinder. So the actual amount was 61 mils. What's the percent air? So in this case, we've got the air amount, which was 6 mils times 100%, and divided by the actual amount. And this gives us a percent air of approximately 9.83%. So keep in mind that if you've got perfect accuracy, there's going to be 0% air if they both measured 61 mils. Now, if one measured 120 mils, you can imagine that the percentage air is going to be really, really high. So think about a lot of these questions logically and what makes sense for these equations, if at all possible. Powder volume, another potential question might come up. So we got a drug, 500 milligrams of drug Y, requires 1.3 mils for reconstitution. If the final concentration of the drug is 250 milligrams per mil when reconstituted, what is the powder volume? So figuring out, okay, we got 250 milligrams per mil, so what do we know? I think you can probably do this in your head. If we've got 500 milligrams of drug and the final concentration is 250 milligrams per mil, that makes sense that our final volume would be 2 mils. Now we added in 1.3 mils of our diluent for reconstitution. So 2 minus 1.3, I think we can easily there solve for the powder volume of the drug. Molecular weights and moles. So remember that 1 mole is equal to the molecular weight in grams. So let's take an example drug here. 1 mole of piperacillin is approximately 540 grams. So that means 1 millimole is equal to, this should say milligrams. Sorry, I goofed up on that. But 1 millimole should be equal to 539.53 milligrams. Okay, don't forget that conversion. 1 millimole equal to milligrams. Now, converting to milliequivalents, we have to look at valence. And so examples here is 1 millimole of sodium, so that's got plus 1 valence, is equal to 1 milliequivalent. But if we happen to have calcium in our drug, so that's a 2 plus valence, that's equal to 2 milliequivalents per millimole. So when you're calculating milliequivalents, definitely remember that. So here we've got an example using that piperacillin. There I got the mathematics right. 1 millimole is equivalent to the milligrams that I talked about. But give a dose of 2 grams of piperacillin. How many milliequivalents of sodium is this? So we've got that 2 grams, which is 2,000 milligrams, and converting that over to millimoles. And then from there, we want to do our dimensional analysis and cross off those labels. Remember that the conversion for sodium is 1 milliequivalent is equal to 1 millimole. So really that's not going to change our answer. But if you had something with 2 valence, then you definitely got to remember to do this conversion factor. That would actually double the amount of milliequivalents compared to the amount of millimoles. So and calculating that out, hopefully that makes sense for you in the way I described that, but you got to remember that valence, and typically they will give that to you. But a couple of common ones to remember: calcium's 2+, sodium's 1+, potassium is 1+, if that ever happens to come up for you. Alcohol USP, this may show up. I did want to throw it in here. Remember that alcohol USP is not 100% alcohol. Okay? So alcohol USP is actually 95% alcohol. So I think that's an important conversion factor to remember. So if prescription is made for drug X in 25 mils of alcohol in the Aura Suite, add a sufficient quantity to 200 mils, what is the percent alcohol of the compound? So whenever we talk about using alcohol, we typically use alcohol USP, which is 95%. It's not 100% alcohol. So solving for how much actual alcohol, ETOH, is in there is what we're going to have to do initially. So recognizing that it isn't a full 25 mils, it's 95% of 25 mils, we get 23.75 mils. From there, we divide that to figure out our percentage of alcohol by our total quantity of 200 mils, and we get approximately 11%, or rounding up, it'd be approximately 12%. Alligation, I would strongly suspect a question like this would come up as far as your math questions go. So you've got 1% hydrocortisone cream and you've got 2.5%, and you want to create a 1.5% hydrocortisone cream. How much of each do you need? So the first thing I look at when I see these type of questions is what are you closer to? And what I mean by that is I look at what we want. So we want 1.5%. And I look at what percent I'm closer to. So 1.5% is closer relatively to 1% than it is to 2.5%. So I know, because I'm closer to 1%, I'm going to need more 1% HCT cream. Okay? So in my final answer, I should have more 1% cream than 2.5% cream. Okay? That helps me. I don't know if that helps you or not, or if that confuses you, but when I get to my final answer, I should see that I have more 1% cream. So doing the alligation method, you start with what you have, you put what you want in the middle, and you cross-subtract out. And so this is the 1%, and this is the 2.5% across. And so we want 1 part 1%, more 1%, and 0.5 parts 2.5%. So solving for that, we want 66% approximately, or a third, or excuse me, 2/3, 1%, and we want a third, 2.5%. So 60 grams times 2/3, or 66.7%, you're going to get 40 grams. And this, again, is the 1%. So taking 60 minus 40, you're going to get 20 grams of the 2.5%. Okay? So that's how I do alligation problems. Hopefully that makes sense to you. And trying to figure out how to decipher these questions. Sodium chloride equivalents. So typically this is going to be used in isotonicity, kind of classically used in something like eye drops. And these drugs, each drug is assigned a value, which is sometimes called an E-value or equivalent value. And that gives you the approximation of how much sodium chloride equivalent that drug is going to contribute to within a compound. So remember that isotonicity is 0.9 grams in 100 mils of fluid. Okay, that's normal saline. That's considered isotonicity. So calculating one of these, so here's a question. We've got drug Z has an E-value of 0.15. How many milligrams of sodium chloride would need to be added to a prescription of drug Z at 2% for a total quantity of 40 mils? We want the prescription to be isotonic. So there's a lot of information packed in there. The first thing I would do is recognize what concentration of that drug that you want. Okay? And so we want a total concentration of 2%, and so that's 2 grams per 100 mils, and we want that in a total quantity of 40 mils. So figuring out drug Z, we want 0.8 grams of drug Z. Now we want to figure out the sodium chloride equivalent. So again, this is 1 gram of the drug is equivalent to 0.15 grams of NaCl. And so solving that, we don't have a full gram of drug Z. For our compound, we've got 0.8 grams of drug Z. So we want to know what is that approximate sodium chloride in grams that drug Z will provide. So solving for that, that'll provide 0.12 grams of sodium chloride. Now we've got to kind of figure out what it's going to take for isotonicity. Isotonicity is 0.9 grams of sodium chloride per 100 mils, but we don't have 100 mils. We have 40 mils. So we want to figure out how much sodium chloride we need for isotonicity in 40 mils. So solving for that X, we get 0.36 grams of sodium chloride. Now we already have 0.12. So we're going to want to subtract out that 0.12 that we have from drug Z and sodium chloride equivalents. And this is what's remaining, 0.24 grams of sodium chloride. So that's going to be what we need to add to get this compound to isotonicity. So 0.24 grams or 240 milligrams of sodium chloride. So hopefully that makes sense. Hopefully those E-values make sense after kind of solving out this problem. Specific gravity. You may see a question on this, so I did throw it in here. Specific gravity is the ratio between density of an object to a reference liquid. So water, for example, water is equal to 1 gram per mil as far as density. That's kind of our gold standard there. More dense substances will have a specific gravity greater than 1. And I think this kind of makes sense. If you've ever held liquid mercury, if you think of something like gold or really heavy metals, they're very, very dense substances. Less dense substances will have a specific gravity of less than 1. They will weigh, or they will feel less than what water is. So the example I threw down there, specific gravity of gold, is 19.32 grams per mil. Okay, so comparing that to the density of water at 1 gram per mil, you can tell that gold is very, very dense.